In Death Valley, California, one of the driest places on the surface of the planet, a sealed box the size of a large lunch container was left out overnight. It contained no fan, no compressor, no battery, and no moving parts. Inside was roughly a kilogram of white crystalline powder. By the following afternoon, 210 grams of clean liquid water had collected in the vessel beneath it. Not condensed from a cold plate driven by a compressor, not filtered from a hidden reservoir, pulled directly out of desert air, using nothing but the difference in temperature between night and day. The powder is called MOF 303, and the chemist who designed it, Omar Yaghi of the University of California, Berkeley, was awarded the Nobel Prize in Chemistry in October 2025 for his work. So if a Nobel Prize was handed out for a material that manufactures drinking water in the desert without electricity, why can nobody buy one? Let's find out. The story begins somewhere that has nothing to do with deserts. In 1974, an Australian chemist named Richard Robson was preparing a teaching exercise using ball and stick molecular models, and began wondering what would happen if those linkages were built at real scale as actual crystals with deliberate empty space inside them. That question was carried forward independently by Susumu Kitagawa in Kyoto and by Omar Yaghi in the United States, and the three of them shared the 2025 Nobel Prize in Chemistry for the result. Yaghi named the discipline reticular chemistry, meaning the stitching together of molecular building blocks into extended crystalline networks. The materials themselves are called metal organic frameworks, or MOFs. Metal ions act as the corners, long carbon-based molecules act as the struts, and what sits between them is precisely nothing. Yaghi did not set out to make water. His group was working on carbon capture and noticed something inconvenient. The frameworks kept grabbing water out of the air before they could get to the carbon dioxide, and they were doing it at humidities where nothing else worked, then giving that water back at surprisingly low temperatures. The nuisance turned out to be the discovery. The first working device came in 2017, built with collaborators at MIT and loaded with a framework called MOF 801, based on zirconium. It functioned down to 20% relative humidity. But zirconium costs around $160 a kilogram, which puts a ceiling on anything built from it. So the Berkeley group redesigned the framework around aluminium instead, at roughly $3 a kilogram, and called the result MOF 303. Field tested in the Arizona desert in 2018, that first passive prototype returned 70 grams of water per kilogram of material over a full day and night cycle. Now, that's barely a quarter of a cup, but the point was never the volume, but rather that water had come out of arid desert air with low humidity. So, what exactly is happening inside that powder? Under a microscope, MOF 303 looks like an unremarkable white crystalline solid. Chemically, it is aluminium hydroxide linked by a molecule called pyrazole dicarboxylate, and the geometry those two components force on each other produces square channels running through the crystal about 6 angstrom across. An angstrom is 1/10 billionth of a meter. A water molecule is roughly 3 angstrom wide. The channel is therefore not a container in any ordinary sense. It is a corridor-sized, so that water molecules fit with very little room to spare. Because the material is mostly hollow, its internal surface area is enormous, and this is the property MOFs are famous for. If you unfold a single gram of a framework Omar Farha's team at Northwestern University developed in 2012, it would cover 1.5 American football fields. Now, MOF 303 is not that extreme. It measures closer to 1,300 square meters per gram, roughly a quarter of a football field, in a single gram of powder. But surface area is not what makes MOF 303 work. What makes it work is the shape of its adsorption isotherm. An adsorption isotherm is simply the curve describing how much of a substance a material holds at each humidity level. Most desiccants have a gentle, sloping curve, taking on water gradually as the air gets damper, which means they never fill properly in dry air and never release cleanly without hard heating. MOF 303 does not have a slope, it has a step. Below 12% relative humidity, it holds almost nothing. Cross that threshold and the pores fill abruptly, and by 20% relative humidity, the material is carrying 39% of its own weight in water. That step is the entire engineering achievement. It means the framework is aggressive enough to strip water out of genuinely arid air, but not so aggressive that it refuses to let go. And it lets go easily because the bond is physical rather than chemical. The water molecules are held by weak attraction to the pore walls, not by any reaction, so nothing has to be broken to release them. Mild warming is enough. Which brings the whole mechanism down to a single fact about deserts. Deserts are cold at night and hot in the day, and that swing is all the energy the system needs. This natural day cycle itself is the entire engine at play here. If you want to truly appreciate the genius of this system, we need to follow one water molecule through a cycle. At 2 in the morning, the desert air has cooled, relative humidity has climbed, and the cartridge sits open to the atmosphere. The water molecules in the air drifts into the channels and stick. By dawn, the pores are loaded. The cartridge is then sealed inside a vacuum, insulated housing, and left in the sun, which heats the powder and drives the molecule back off the pore wall as vapor. It cannot escape because the housing is closed. Instead, it meets an aluminium condenser, shaded from direct sunlight by a reflector and therefore substantially cooler than the powder. And there it returns to liquid and runs down into a collection vessel. The performance figures of this tech come from a paper published in the journal Nature Water in July 2023 by Yaghi's group. They built the harvester around a stack of MOF pancakes, the powder blended with a small amount of graphite so it holds its shape and conducts heat, space to let air move freely between the layers. They tested it in 2 places. In Berkeley, it produced 285 grams of water per kilogram of MOF per day. In Death Valley, it produced 210. Both figures were achieved with no power input whatsoever beyond ambient sunlight, and both roughly doubled the group's previous passive design. A separate device, reported in ACS Central Science in August 2019, reached 1.3 liters per kilogram of MOF per day. That version used solar panels to run a fan and a heater so it could complete dozens of adsorption cycles daily instead of one. It is a better machine, but it is not a passive one. Regardless, atmospheric water tech like this represents a huge opportunity for water independence. The United States Geological Survey puts the water held in the atmosphere at any given moment at around 12,900 cubic kilometers. The world's rivers hold roughly 2,100. That means that there's something close to 6 times as much water floating above the landscape as there is running through it. It is simply distributed at a concentration of a few grams per cubic meter, which is why extracting it has always been the problem rather than finding it. Now, it's worth remembering that Yaghi's frameworks are not the only approach to harvesting the floating reservoirs of water. In June 2025, a team at MIT led by Xuanhe Zhao published in the same journal a device they call an atmospheric water harvesting window. It looks like a black vertical panel about the size of a window, filled not with a metal organic framework but with a hydrogel, a water-absorbing polymer loaded with hygroscopic salts and molded into small domes that swell and collapse like origami as they take up and release moisture. This thing was also tested in Death Valley, and it produced between 57 and 161.5 milliliters of water per day across a relative humidity range from 21% to 88%. With a working life of at least a year and lithium-ion concentrations in the output below 0.06 parts per million, that last figure matters, because salt-loaded hydrogels have historically leached their salts into the water they produce. Then, of course, there is the oldest method of atmospheric harvesting, which is not adsorption at all. Fog collection uses nothing but mesh. A study published in Frontiers in Environmental Science in February 2025, led by Virginia Carter Gambarini and Natalie Verbrugge, spent a year measuring fog capture around Alto Hospicio in Chile's Atacama Desert, where annual rainfall is under 1 millimeter. Standard 1 square meter collectors, which are simply Rachel shade mesh on a frame with a gutter, yielded between 0.2 and 5 liters per square meter per day, peaking at 10 liters in August and September of 2024. The researchers calculated that 17,000 square meters of mesh would cover the 300,000 liters a week currently delivered to the city's informal settlements by truck. That is a staggering return for a material that costs almost nothing. But the catch is geographic and seasonal. The fog runs from May to October, and the productive sites sit on higher ground outside the city limits. While fog harvesting nets may not be suited to every climate, at least they are currently commercially available, unlike the MOF harvester. Right now, there's no commercial option to buy one of these things, and there are some pretty compelling reasons why they're not ready for mass adoption yet. First, there's the yield. 210 grams per kilogram per day means that a passive cartridge holding a kilogram of an expensive engineered crystal produces slightly under a cup of water every 24 hours. A single person's drinking supply needs roughly 10 times that. A community-scale machine therefore needs its MOF, measured in tons, and passive operation caps the cycle at 1 per day because there is only one sunrise. Then there's the real bottleneck, which is not performance at all. The physics has been validated for the better part of a decade, but what has not been solved is manufacturing metal organic frameworks cheaply, at scale, without toxic organic solvents. The frameworks work. The factory does not exist yet. And then there are the numbers that end most of these conversations. Paul Westerhoff, a researcher at Arizona State University, has estimated that drinking atmospheric water would cost him around 10 times what he pays his city for tap water, and more than water produced by desalination. Conventional atmospheric water generators, the kind that chill air to its dew point, typically consume between 0.3 and 1 kilowatt-hour per liter depending on climate, and a year-long field study of one commercial unit in Sharjah measured 2.25 kilowatt-hours for every liter it made. Adsorption is a route around that energy cost, not an abolition of it. But not everyone in the field thinks the effort is well spent. Christopher Gasson, a water industry analyst, has argued publicly that atmospheric harvesting is a distraction, and that the serious work lies in using the water already taken from rivers and aquifers more carefully. The honest structural reason, though, is subsidy. Municipal water in most developed countries is priced against infrastructure that was paid for decades ago, not against what it would cost to replace. Anything competing with a tap is competing with the most heavily underpriced commodity in the house, which is precisely why the first customers for this technology are not homeowners. They are data centers in arid regions, hospitals, remote industrial sites, and disaster response, where the honest alternative is not a tap, but a truck. So, should you be preparing to install a MOF harvester for your home? No, not this year, and probably not this decade. The emerging technology is extremely exciting, but currently there is no consumer product. Yaghi founded a company called Atoko in 2020, based in Irvine, California. And in April 2026, it demonstrated a commercial prototype to Bloomberg. A 20-foot shipping container producing up to 4,000 liters a day on grid, or up to 1,000 liters a day off-grid, with output close to distilled quality and free of PFAS and microplastics, because the framework absorbs water molecules and essentially nothing else. Now, as of that reporting, the company was not yet taking orders, but they are expected to build and sell 200 machines in the coming year. Pricing has not been disclosed, beyond a stated ambition of a few cents per liter, which the company itself acknowledges is more expensive than desalinated water. A comparable MOF unit from the British firm Obstra, the ARK, is listed at £150,000 for up to 500 liters a day. So, while this tech might be a while off for most of us, for the homeowner wanting to start securing their own water supply, they should start by catching the water that is already falling on their roof. 1 millimeter of rain landing on 1 square meter of surface delivers 1 liter. A 100 square meter roof, in a climate receiving 600 millimeters of annual rainfall, therefore intercepts around 60,000 liters a year, in theory, and realistically 45 to 50,000 after gutter losses, first, flush diversion, and overflow. That is 2 to 3 orders of magnitude more water than any atmospheric harvester you could buy for the same money. And the equipment is guttering, a leaf filter, a first flush diverter, and a tank. And if your climate delivers coastal fog, the second option is a Rachel mesh collector on a frame, which is the cheapest water technology in existence, and which the Atacama data suggests can return several liters per square meter per day in the right terrain. Neither of these requires a Nobel Prize, and both are available right now. So the MOF frameworks are not a fraud, they are simply early. The chemistry that took 50 years to invent is now waiting on a supply chain that will take rather less time to build, and the day itself remains the cheapest engine anyone has found for driving it. This is not a little box you put on your yard. It's a serious piece of infrastructure that has not been built yet. If understanding how buildings and landscapes handle water, heat, and air without machinery is the kind of knowledge you think should keep being found, subscribe, because that is the entire purpose of this channel. And if the 60,000 liters a year falling on an average roof caught your attention, then make sure to check out our video on the most innovative tech that you can implement right now to maximize your water harvesting efforts.